5 seconds. Okay. Welcome to the Computer Security Seminar from Purdue University. Today's speaker is Ari Takanen from Kodonomicon, and he will speak on robustness testing, black box testing for software security. Okay. Ari?
Thank you. So my focus here is robustness testing, and reason for that is that Codenomicon is a spin-off company from University of Oulu. University of Oulu has been researching software security since around 1996 and has extremely narrow research focus in that sense that their interest area is on software flaws caused by software programming errors. So we call those implementation level security problems. So software security is the main topic. Codenomicon itself is a software company doing quality assurance tools. Contents of this presentation are as follows. I will start explaining software security. I know most of you already know that the topic quite well, so I will go quite quickly through it. Then I will focus on security testing, different approaches of finding security problems proactively during product development, especially testing phase. Then I will go into more reactive approach of software security, covering issues related to finding problems, reporting problems, getting those problems fixed, and getting those fixes deployed into the real users of software. I will conclude with few comments afterwards. So, starting from software security. Security as a topic is extremely wide, covering everything from viruses, encryption, authentication. Software security as a focus area from that area takes the smallest building blocks of networks of software, meaning pieces of software actually doing, for example, communication, being responsible for communicating with external world, being the building blocks of, for example, hardware devices, network routers, actual business perspectives of networks. So software has different responsibilities and different risks associated to that. In general, software security flaws are always bugs in software. They can be resolved by fixing the software so that those bugs are eliminated. Any software flaw that is critical in that sense that it causes the software to crash, hang, cause delays, take more memory, have memory leaks, all inputs causing these kind of flaws are always security related. So if you analyze any software development project, bug database, from security perspective, all critical flaws are always security flaws. Biggest difference between quality assurance people and security people is that a quality problem in software becomes security problem if it's known by someone else outside that organization. Until that time, it's a quality problem in a software, and it can be prioritized according to standard bug prioritization principles. Some vendors prioritize security problems as one own category, but usually they are just critical flaws. They have to be fixed as soon as possible, especially fast if someone else knows about the triggers, how they can be actually misused. Any software flaw well, the typical reason why people are motivated in getting rid of them is that you can deny service. As security researchers, many people start analyzing what other error modes you have in relation with security flaws. But considering those from developers' perspective, it doesn't matter. You have a flaw in software which can be used to enter, to take control of the system, to modify data, to eavesdrop data. And if you eliminate those flaws as early as possible during the software lifecycle, you save money. Not only because of losing money, because of losing data, losing public image, public, well, everyone knows what people think about some companies' products. You stop trusting the technology, you stop trusting these software manufacturers because of security problems. And when you start eliminating these problems, you have to decide whether you go for reactive tools or proactive tools, whether you prepare for the worst or whether you start investing in actually fixing the problems during programming phase, following secure programming practices, in testing, in different risk equations, just preparing for the losses. In the past, especially at the turn of the millennium, there, for some weird reason, became a trend of finding and reporting problems in software publicly. So every time someone found a bug, a security problem in software, for some weird reason, they wanted to publish it. They wanted to get fame out of that problem. So the value in that also was that people became more aware of these problems. Before that, there were only few people who knew about security problems, what were the actual technical issues behind them, and also becoming aware of different security problem categories enables engineers to learn from mistakes not only made by themselves, but others as well. But from security perspective, if someone knows about a security problem, they can always misuse it. It doesn't require you to have the actual exploit or source code to the problem. It's only a matter of minutes or hours or days that someone can always find what the problem actually was and create exploits for that, or worms or viruses to exploit those problems. Most of these problems are because of programming errors, simple mistakes made by programmers during the software development. If you look at different categorizations for software flaws, security-related software flaws, there really isn't a consensus on how to categorize them. Many people try to categorize them on based on failure modes or exploitability or different kind of categorizations for the attacks themselves. But the most important issue here, for example, in this example of a statistic, is that configuration errors, design errors as a category are quite small compared to the rest. So if you divide them into three major categories, design errors are something between 16 to 30%, configuration errors only in a range of 5 to 8. All the rest are implementation errors. They are made by programmers who were not aware of the consequences of making that choice, either in a function they were using, a code construct they were using, or so on or so on. It's not improving either. So everyone knows what's happening to software, what's happening to processing power. You can have even mobile phone handsets that have the same processing power that PCs used to have in the past. And the software in them as well is as complex. The more complex software you have, the more programming errors you will have, and the more you will have also those that are security related. So software complexity, communication interface complexity, those all drive towards having more security problems as well. When you have communication standards, when you have standards how software interacts, it also enables that one attack can attack software developed by different vendors. It also means that if one vendor has a monopoly in some situation, it definitely will attract worms. So if you are imagining what are the next playgrounds for worms and virus-like attacks, you can see it from the penetration of software. It can be a cell phone manufacturer, it can be an antivirus manufacturer, it can be anything that you have or most of the people have installed on their communication devices. All networks are merging together. Everything is internet connected. You can control nuclear power plants over internet. You can make voice over IP calls to traditionally closed networks. Everything is nowadays internet connected. And devices are also scattered around. You don't know where the actual attacker is. You don't know who it is. You don't know what kind of device they are using. So there will be lots of work on the security area in the future as well. Security testing is one category where you try to eliminate the number of security-related problems in software. You cannot get rid of all bugs, but you can prioritize them. You can make risk analysis and try to get at least the worst ones out as early as possible. What we have nowadays is different kind of, for example, certifications. So if you are developing, for example, a device or building a network, you can certify it to be of some accepted security level. Most of these certifications have nothing to do with software quality. If you take common criteria, for example, it only verifies that you have the listed security mechanisms present. It doesn't go into analyzing the quality of the software. It's going there, it's getting there, but it's not at the moment. Telecommunication terms like carrier grade, which means that the box should be as stable as possible. It has like 5 nines or 6 nines of reliability. But if you consider that from security perspective, one flaw is all it takes, and anyone, anywhere can disable that box repeatedly. It doesn't really seem like a reliable device when you are connected to hostile networks. It might apply if you have a machine room in a closed network with big letters on the box saying don't touch, and it might stay up that reliably, but not in hostile networks. Some metrics of security or product security come from, for example, penetration testing or hacker testing. So if you measure, if you take a bunch of consultants or security experts and ask them to revise or measure the security of a device or software, how you can do that is measure their motivation, how much money you give them, skill, time, and from that equation get an assurance level, how much motivation, skill, time the, for example, hackers would require to find similar kind of problems. So if you can give them a year and think that hackers also will start looking for easier targets after spending that much time on it. Of course, it means that the people you are protecting against will find other easier targets. Some people might be so motivated in finding problems that they just don't give up. And then these metrics don't apply. Learning from quality assurance tools in general, when you take an engineering approach to it, you start developing automated testing tools for repeated and neutral approach for comparing the security. Different security testing types can be simply categorized in black box testing and white box testing. You have levels of gray in between, but simplified, you have black and white box. In black box testing, you don't care about the source code at all. In white box, you take all benefits that you can have from the availability of source code. These are numbered from 1 to 6. Unfortunately, that's also sometimes the case how people prioritize these. Everyone does conformance testing, at least in some sense. They verify that requirements are fulfilled. If you promise to do something, you also do that. When you start doing conformance against industry standards, for example, security standards, then you get into security testing as well. But otherwise, if you stop at verifying that you have the necessary functionality, you don't do security testing at all, except for verifying the security mechanisms. Performance, on the other hand, verifies that you can stand a heavy enough load in real-life environment. So it's repeating one of the conformance tests as fast as possible or in parallel. Robustness, on the other hand, or security, robustness testing is much better term, tries to inject all possible unexpected inputs to the software. So when conformance tests are traditionally considered positive tests, robustness tests are negative tests. Both of these have been used in the past, but dividing them is necessary at this point. On white box area, you have code auditing. It's always essential to do. You have fault injection. It's done in some expensive software projects, meaning you, for example, inject faults in the code or inject faults into modular or process communication to find out the reliability of the software or component. Formal proofs, even more expensive, means that you actually verify that, for example, encryption algorithm is really robust, secure. Auditing code, typically done manually, meaning you have code inspections, reviews, but hopefully in the future more automatically. In code auditing, the most important thing is that you know what to look for. So it's all the same if you have thousands of open source developers looking at the code. If they don't know what the security problem looks like, they will not find them. So essential in both code auditing tools and auditors, people, is that they know what to look for. You can have checklists, you can have courses on secure programming, you can have different kind of means of collecting that data from past experiences of others. But basically, they look for structures in code that are known to be problematic. In black box testing, you don't have the source code, or you have it, but it's just too huge to go through using code auditing tools. Many of the code auditing tools even generate so many false positives, alarms that are not true, that you just spend all your time reviewing those. It's impossible if you start doing it at late phases of the software development project and with huge amount of code. Sometimes you don't have any expertise in secure programming, you don't have the people, you don't have enough people to review the code, or you don't have any experience in having mistakes in your software. If you have quality assurance processes in place, you have to learn from your past mistakes. If you don't have any past mistakes, you don't have anything to learn from. For example, programming languages like Java, Symbian, many of these new next generation languages, there are same kind of problems, but no one knows about them. You have to first collect experience from past mistakes to know and learn from them. So, learning from other people's mistakes, also enabling testing different communication products using the same interface means that black box testing is quite useful there. Penetration testing is quite widely used. There are lots of consultative companies who do penetration testing. And it's also an area where you have to be extremely careful, because many of the consultants don't do anything else but review for known errors. So they are doing either manual or automated verification that you are not repeating someone else's products, someone else's problems. So if you, for example, take security scanners, it's a common security tool. What they do is same thing as virus scanners. They look for known fingerprints of problems. And if, for example, a past version of a web server contained a problem, verifying that the version number of the web server is higher than that is not what security testing is about. Security testing is about actually trying out all those inputs that cause problems. And that's not what security scanners are for. Security scanners are administrator tools. Performance testing always finds security problems. There is always a load that will drive the system down. Only solution there is to measure what is that load, be prepared for it, divide the load between servers, just put more iron on the border. Robustness testing as a category is functional testing, so it's actually trying out functional operation of the tool or product, but it's using fault injection principles in actually injecting anomalies within the communication sequence. So communication can be between internal modules, operating system and the software, network, files, hardware, and most commonly users or network. And always when you start analyzing a software or a system, you start from risk analysis. The most open interface you have defines how open your system is. If you are making a web server, it doesn't matter how many firewalls you have in front of it, if they allow web traffic through. So it's as open as all the communication, most open communication interface you have. Simplifying security testing or robustness testing, you have, for example, if you have a security mechanism like authentication, you have username and password combination that is required to get in. Conformance tests at minimum have to try that your authentication works. Performance testing at minimum is trying repetitions of logins or parallel, how many parallel users you can have at the same time. Negative testing, hopefully in the future, will be more part of conformance testing, so that you have verified, you have specified at least a set of negative tests that have to be tried as well. You cannot enter the system by using wrong password, you cannot enter the system using someone else's password, and so on and so on. But when you imagine what all kind of inputs even this simple interface allows, you can imagine how wide the area of robustness testing typically is. You have to try long strings for buffer overflow problems. You have to try different kind of structural modifications. You have to try all special characters that might be used in databases behind the authentication, in files that might be used in some components of the software, and so on and so on. If you analyze different critical interfaces that systems nowadays have, we can start from voice over IP, for example. It's the gateway to traditionally closed critical networks. So if someone is calling over the IP unidentified person towards a critical system on the other end, you are opening traditionally closed system through it. Web, always, there are lots of business critical applications running on top of web, internet. LDAP, well, it's quite critical. SNMP, simple network management, was actually one of the issues which made University of Oulu research popular, because everyone has it enabled. It's in everything ranging from network cameras to missiles. VPN connections, encrypted communications. it's still a communication protocol. It might be a tunnel, it might be encryption in different layers, but it's a complex communication protocol, and it's extremely complex communication protocol, meaning it's extremely error prone as well, even from security perspective. Radius, TACAX, authentication, routing protocols, IP protocols, everyone knows about few individual problems like ping of death or so on or so on. But you have all these same problems in all IP stacks, all possible devices implementing IP. It's not just the common operating systems. All network services, the surprisingly complex protocols in industrial automation and so on. Cars have networks inside and so on. All of them are critical, either from openness perspective or being single points of failure within networks. If authentication fails, it means that no one is communicating that day. Measuring test coverage first starts from analyzing those interfaces that you have. Then when you are doing testing, you can use different kind of metrics for code coverage or branch coverage, how many of the security requirements you have verified and so on. But when you consider the whole input space that can be given to the communication software, you get an infinite space of inputs that can be given. So it requires a new metric, and if someone is interested in researching that, it's a really interesting topic, and there isn't much research on that topic. One basis for starting could be, for example, communication protocol standards. So if you take IETF specified TFTP as a simple example, it's only protocol consisting of 5 elements. You have extremely easy machine readable format for actually passing it through, to teach it to a test system or script. You can describe it as trees, format of something that you can traverse through and actually generate test cases from it. So even a simple protocol like this builds up a little tree that you can generate all valid cases. You can generate all valid use cases that can be imaginable here. And there are products doing that actually. But it's easy to do. When you add all possible anomalies that you can use in addition to legal values, you get much wider tree already. So even a simple protocol like TFTP typically has in range of hundreds or thousands of test cases for negative testing. But if you imagine a simple protocol like this from brute forcing perspective, if you are breaking a key that consists of this many bytes, how much time does it go to go through all possible combinations, just brute forcing all the possible input combinations to it? So of course you can take a fuzzing way. You can just insert random data. Given enough time, you will cover all the possible combinations, but it will take much more time. So knowing data structures, knowing possible contents to actually find these problems helps a lot. When you decide what was the actual result from the test execution, you get into differences why conformance testing has to be separated from robustness testing. In conformance testing, you always verify that all replies are according to the specification. So if the reply is wrong, then it's not a valid, it's a failed test case. In performance testing and in robustness testing, if the test sequence doesn't crash the software or cause memory leaks or performance problems, then it's passed. But if it crashes, if it causes some other selection criteria for failing, if it fits into that, then it's a failed test case. So you don't analyze all the responses, and that's usually even impossible because according to standards, in some cases, if you send non-conformant messages, it's equally valid to just drop the input and ignore it. In some cases, it's equally valid to give an error message. In some cases, you don't want to give an error message even if it's required by the specification, just because of security reasons. So you don't have to have an oracle to verify all the responses. Where can you use security robustness testing? You can do certification, software development. That's the best place because the earlier they are fixed, the better. But unfortunately, many software developers nowadays are not interested in security. They don't have the motivation. They don't have the economics to actually calculate what kind of investments are required for secure development. So in those cases, you have to actually go to the end users. If you have operators, governments, banks who actually know what's the damage when they have security problems, they want to do the risk analysis and acceptance testing as well. And these are the market areas for security consultants. If you look at robustness testing from real-life examples, here's an example from University of Oulu webpage. It's showing test results from testing 9 commercial products that are communicating using SIP, which is voice over IP protocol. Test grouping is based on structures within the protocol itself. You have different header fields, you have different structures within the communication protocol, and you are trying different kind of broken structures within those. It's difficult to categorize these failures, but basically, if you have a product failing in all possible test groups, test categories, it means that hackers would have easy thing to find a problem also in that kind of product. In worst cases, 50% of the test groups or 50% of test cases found a problem, security-related problem. And that means that developers don't have a clue how to program network communication software. In some cases, maybe because of using Java or some other more reliable programming languages, they get less problems. But still, there are extremely few products that don't have any problems at all, no matter what programming language, no matter what operating system, and so on. And even products from the same vendor have huge differences because it's still because of people making mistakes, and you have different kind of people in different development teams. You have different kind of software development practices in different development teams. When you have a group of 10 to 1,000 of test cases, it doesn't mean that all the test cases within that group find problems. Sometimes you can have, for example, in the username password combination, if a valid username would be less than 8 digits, characters, then software might survive tests until, for example, 100, 200 characters. 201 causes a crash, 202 again survives. So it requires more than 1 to 10 test cases to find different kind of problem categories. And it's not every test case within the group that finds a problem. And when you find a problem, then you have to verify what kind of problem it actually was. Here we have TLS handshake, and on red is actually a length field within TLS handshake message. So defining different length within the packet compared to the actual content can cause the software to allocate too much memory and crash and fail, trying to read more data than actually fits into the buffer. Typical buffer overflow, but it's based on actually having wrong length values in the protocol. So in here you have ASN1 kind of structure, but it's not ASN1. So you have type version length specifying the packet, and length in this field is actually showing much larger than the actual content in the packet. Systematically going through all fields within protocols, no matter how they are specified, whether they are ISN1 or ASCII based or IETF specified. You have to go through all the data types and use all known inputs that can cause problems there. ASCII-based protocols, just the same. So you have a structure that contains lots and lots of different header fields. Within there, you are inserting line fields just in an unexpected place. And in this case, Java application crashes. I don't know why, but it crashes. Or one problem category is loops or repetitions. So you have, again, a complex protocol structure. Within there, in one field, you are repeating a structure that wasn't supposed to be repeated. And again, you can imagine from programmers' perspective how they would implement this kind of a parser that just keeps on going and never ending a structure. It can either just reserve all the memory or it can just end up in a buffer overflow again. Security testing and testing in general has always limitations. You can never find all security problems by testing. You can never find all security problems by auditing. Performance testing always finds its own category of errors. You can combine different means of testing. You can run the software under heavy load and then do conformance testing, negative testing, and so on. There's different combinations how you can benefit from it. There's lots of gray box testing tools. There's different tools how you can actually monitor binaries. You can analyze what's actually happening within the software to help you in discovering these problems. And it's all up to actually using risk analysis and best effort in trying to find the problems. I will now talk a little bit about what happens to the rest of the problems. You cannot eliminate all of them by auditing and testing, so what happens to the rest? If someone finds a problem, you have a communication network. You have someone containing often confidential information that you want to have, and usually using some confidential communication channel. So you have finders of the problems, for example, Tiger teams, whether inside an organization or external Tiger teams. You have your own or outsourced or external response teams or coordinators, and you have the actual developers who are responsible for fixing the problems. There are different ways of handling these. If you find these problems internally, you have always the option to do no disclosure at all. So you just fix the problem quietly and forget about it. Don't notify anyone. If the discoverer is using no disclosure policy, hopefully he is disclosing the information at least to the developers. But still, many security companies never expose any of these details to general public. In some cases, especially commercial companies, they disclose partial information about these security problems. In worst case or best case, depending how you see it, they just notify that you have a problem, please patch. Please install these corrections to get rid of it. From attacker's perspective, it makes it difficult for them to analyze how to actually create an exploit against it. But it's not impossible. For users' perspective, if they believe software developers enough, they will install the corrections anyway. If not, it's difficult for them to make their own risk assessment. Full disclosure, always with open source, means that all details are public. You can even review what was the change actually made to the source code. In some cases, reporters include an exploit also. Exploit is extremely fast available, meaning you can easily abuse those problems as well. But simplified or not simplified. The whole process of someone finding a problem to actually resolving it includes a lot of communication. Even when you are communicating with only one software developer, maybe some coordinating organization like US CERT or some other incident response team, at minimum it usually takes tens or hundreds of emails or telephone calls to get the issue resolved. In some cases, it's thousands of emails and communications. But still, it's a process, and if it's a process, you can describe it, you can study it, you can make analysis of how it proceeds from originator's perspective, finder's perspective, coordination perspective, and repairer's perspective. Extremely interesting research topic if you are interested in this. In communication, vulnerability communication, you have lots of problems. As I mentioned, the biggest one usually is the volume of communication. Many of the people just don't want to get involved with it. Trying to convince people that you really have a bug, trying to convince them that it really is a security bug, it really is critical. Sometimes no one can reproduce what you found. Sometimes developers fix it, but you can easily find a way to actually abuse the same problem again. So it's like just looking at one line of the code, fixing the exploit actually, and not fixing the whole problem. Sometimes you are happily resolved the issue, but then suddenly notice that the same problem is in products of hundreds of other vendors. Same bugs come again in that sense that some people just copy and paste code from legacy systems. In some cases, they just branch products and fix only one branch. And worst thing usually is also that sometimes people don't want to upgrade their systems without actually having high enough risks involved. So you need to have exploits to motivate customers, motivate users to upgrading their systems. That's not a really good thing. I will conclude with few slides. Software security is software quality. So most of the problems are software quality related. Most of the problems that at least are abused out there are quality related. Every now and then someone breaks crypto, and that's nice, that's interesting as a research topic, but it's not where most of the problems are. You have to have good crypto, but when you have it, most of the problems will come from actually implementing the crypto. If you have 4 nines, 5 nines, 6 nines reliability, you still are 100% vulnerable if you have one problem there. So doing risk analysis in a system starts from analyzing, identifying all communication interfaces, critical sections within networks, and studying the openness, complexity of the interfaces, studying how much of the software itself is exposed out of these communication interfaces. Then it's a process of testing, reanalyzing, and reiterating the whole cycle again. You will never get rid of all the problems. Problems will come back. You cannot just end it in one cycle. I will end with some words from Boris Pager, who is quite famous testing engineer. In security testing, as in quality assurance in general, testing is important. Testing is extremely interesting topic of research as well. And it's really unfortunate that today, if you cannot code, you become tester. So it's not like quality attribute. Good testers are really good testers, and they are better usually at it than anyone else can be. And the better tools you have there, the more effective you can be. The more automation you have, the more effective you can be. So you can kill the interest of testing by having bad tools as well. But testing is not to cause harm to the organization, it's to help programmers. That's it. If you have any questions, I'll be happy to answer now or later on. If you want to contact me later, I can provide contact details to you.
Yes. You mentioned at the beginning of your talk common criteria. You said they didn't include metrics of software or even consideration of software quality. Is there a suggestion you could make for that?
I know of at least one common criteria certification where robustness has been taken into consideration. It's I'm not sure if it's a standard, but it's a robustness profile called addition to common criteria. So as long as you don't have standards to test against, you cannot have certification for robustness either. So there are some organizations like IETF, ITU, other bodies who are responsible for standardization of software or protocols or specifying protocols, who are actually specifying robustness tests as well. That could be one solution there. So then common criteria can verify against a set of tests that have to be implemented or have to be passed. But otherwise, if you consider specifying in common criteria that you have to have 4 hours of fuzz testing, it's not a really good criteria. Or you have to have this level of penetration testing. It's difficult to measure and difficult to certify.
Okay, so you were not referencing software quality metrics that some people generate for us. You were referencing robustness testing, or that would be your preference as a way to include software quality in the common criteria.
Yeah, so if you have certification, you have different criteria for certifying it. You can have conformance to a security standard, for example, torture tests by IITF. So it's a set of tests for testing robustness. You can have a set of accepted performance testing, for example, for common criteria. And you can have accepted level of penetration testing, but it requires a metric there. It can be based on standard quality assurance metrics like code coverage, branch coverage, and so on, but it has to have a metric.
Any other questions?
Okay, let us thank the speaker then.